Today we're going to talk a little bit more in depth specifically about what a system of equations is, and what we're going to be able to find today is the solution to a system of equation. So in general, think way back to Unit 1. When we talk about a solution to any type of equation, it could be a linear equation like we looked at, or a linear inequality. A solution to a linear equation means a value that makes the equation true, right? So if I have a very simple equation, x plus 1 is equal to 7, well, I know I can solve that. I can subtract 1 from both sides. We would get x to equal 6. So I know 6 is a solution to the equation because when I substitute 6 back in, I get 6 plus 1, which equals 7. I know 7 equals 7. That gives me a true statement. So therefore, 6 is a solution to the equation. So that's going to be the same thing when we look at solutions of systems of linear equations. And all a system of linear equations is when you have two or more linear equations that we put together on one graph or look at it on one time. And again, that's called a system of linear equations. And we're going to look at them today specifically on a graph. So when you have two or more linear equations together, like we looked at yesterday with the taxi cab driver, that is a system of equation. So the solution to a system of equation consists of the x and y values that make both equations true. So in the example that we looked up above, that this little equation x plus 1 is equal to 7, there was only one solution, there was only one answer, right? We only looked for the x value. But now we're going to have two equations, and they're going to have x and y, so we're going to look for both of them. And when we're looking at a graph, like we saw yesterday, again with that taxi cab, we know that graphically this is going to appear as the point where the two lines intersect each other. So if we have a graph, awesome, we graph one line, we graph the other, and we find that point where they intersect. Perfect. That is what we are going to be doing today. So again, if you're not given a graph, or if we are just given a question like number 5, which we've seen things like this before, number 5 says, how could you check to see if the point 5, negative 1 is a solution to the system of equations? So here are two equations. This is our system. Sometimes there'll be this squiggly bracket in front of it. Sometimes there'll just be two equations listed like this. So if we want to check to see if the point is a solution to the system, that means that the point has to be a solution to both equations. So I have to plug 5, negative 1 into both of my two equations and say that, yes, it's a solution for both. It's not enough to say it's just a solution for one. So I'm going to start with that first equation. X minus 3y is equal to 8, but instead I plugged in 5 for x and negative 1 for y, and I'm going to simplify. I know 5 plus 3 is the same thing as 8, so therefore my point 5, negative 1 is a solution of the first equation, but now I have to check my second equation as well. 2x plus y is equal to 7. I plugged again that same x and y in for my into my equation. So now here I get 10 minus 1 is equal to 7. Uh-oh. This is not going to be a true statement. So even though my point was a solution for my first graph, it was not a solution for the second graph. So therefore, it's not a solution of the entire system of equations. It's kind of like the taxi problem from yesterday. Maybe you made you had the right amount of shifts, but you didn't make the right amount of money, so we can't say it's a solution to the system. So now let's look at how we find some of those solutions by looking at the problems on the back. Just kidding, I forgot these on the bottom. Number 6, 7, and 8. So a solution to a system, again, it's going to be the point that you can plug in that makes both of the equations true. Or we said graphically, it's the point where the two lines intersect. So if I just have any two lines here on my graph, if I have one solution to the system, that one solution is going to be that one point. So that point right there that I highlighted in red would be one solution to the system of equations. Two lines on the same graph, the point where they intersect is the solution. A system that has no solutions would mean that the lines never cross. Well, what kind of lines never cross? I know you're all saying it right now. That would be two parallel lines. And we're going to look more closely at those parallel lines in this unit, but two lines that would never cross, that have no solution. There's not a point where they intersect, parallel lines. And then infinitely many solutions. This one's kind of tricky, but we learned a bunch of different forms in our last unit. We learned point-slope form, we learned slope-intercept form, we learned standard form. And we had a couple questions that asked, are these two equations equivalent? And we had to maybe simplify one, change one into slope-intercept form, and see whether or not they were actually the same equation. When they are the same equation, that is when we would have infinitely many solutions. So maybe I gave you this equation in slope-intercept form, and you graphed it, and then I gave you an equation in slope-intercept or in point-slope form, and we graphed them. It turns out that it looks like it is one line. That's how you know that the lines are equivalent, and they also would have infinitely many solutions. That means they intersect everywhere, right? Every single point on this line here are going to be points where my lines intersect. So this is what we say, it has infinitely many solutions, or our solutions are all real solutions. So those are the three situations that we're going to run into in this unit. Now let's look at some examples on the back. Number 8, both of these two equations are in slope-intercept form, which is really nice. It says graph the system of equations below and find the solution. So I'm going to start by graphing my first line. Again, it's in slope-intercept form. I know my y-intercept is -4, that number at the end, and the slope is -7/4. So I'm going to go from this point, I'm going to go down 7 and to the right 4. So it would be that point right here. It does go off the graph just slightly. There's not enough room to go all the way down 7. But I know I also can go in the reverse. I can also go up 7 and to the left 4. So there is point number 3, and I can keep going if I need to and draw a line between my points, and that is the equation that is that first equation graphed. Now for my next line, I'm going to graph it on the same graph. That's going to be in the orange here. Same idea, it's in slope-intercept form. My y-intercept is 1, and my slope is -1/2. So I go down 1 and to the left 2. And I want to make as many points as I can to show where my lines are going to hopefully intersect. So I'm going to keep going up and to the left, and I can see right there I had a green point there and I have an orange point there. So that point right here is where my two lines are going to intersect. So that is my solution. So again, that means I have one solution because they cross, but my answer to this question, the solution to this problem, are the coordinates of that point. So that point is -4, 3. So my solution, wrote that backwards, is -4, 3. That is the answer to this problem. I'm going to skip down to number 10 because number 10 I can see down there has a equation in slope-intercept form and it has one in standard form. So I just want to double check that we remember how to do standard form. So again, my first equation is in slope-intercept form. Nice and easy there. I know my y-intercept is -4. I know my slope is 3. So I can graph some points on that line and draw a line between those points. So there's that first equation. My second equation here in that standard form, we need to manipulate somehow to be able to get points on our line. So remember, you have two options. Number 1, change it to slope-intercept form. Number 2, plug in those zeros and find those x and y intercepts. I'm going to plug in the zeros so we can find those x and y intercepts. So I plugged in 0 for x for my x, plugged in 0 for y for my x-intercept, and plugged in 0 for x for my y-intercept. And I can solve both of these tiny two equations. They're going to have the exact same work because they both have 4's attached to them. So I get 3, 0 for my x-intercept, and I get 0, 3 for my y-intercept. So I'm going to graph those 2 points. And we have those 2 points. I can keep going. I want to follow that same pattern because I want to find exactly where those points cross. So I know my slope between those 2 points. I'm going down 3 and to the right 3, which is the same thing as -1. So my slope is -1, so I can kind of fill in lots of points there, and there we go. We have a point that both of my graphs have in common. That point is right here in that middle. That point here is at 4, -1. So that's how we graph a system of equations. I encourage you to try to do number 9 and number 11. Don't worry about 12 and 13. They're actually the same two problems as 10 and 11. So go ahead and pause the video for a couple minutes and try and graph number 9 and number 11. Come back and check your answers. I'm going to reveal those answers in 5, 4, 3, 2, 1. So number 9, the solution is -2, 2. Both of those equations are in slope-intercept form, so the point where they cross is -2, 2. And number 11 at the bottom was a little tricky. The first one's in slope-intercept form. I decided for number 11 to change it to slope-intercept form. Again, you could have found the intercepts and done the same process that we did in number 10. But when I change it to slope-intercept form, I can see that, in fact, these two lines are never going to cross each other. We're going to learn this a little bit later, but they have the same slope. So therefore, they're never going to cross. You can see in their picture they never cross. So the answer to this is no solution. Thank you for watching. Now continue on and get some more practice on Delta Math.